Hello, how are everyone? Welcome once again to another seminar of the IAG Astronomy Department seminars. Many thanks for joining us. And today's speaker is Dr. Paola Di Matteo. Many thanks, Paola, for accepting our invitation and being here with us today. And Paola got her PhD from La Sapienza in Rome in 2005. And after, she worked as a postdoc at the Paris Observatory, where she's an associated astronomer since 2011. And Paola's work is focused on the study of the formation and evolution of the Milky Way and its stellar populations. And today, her talk is entitled Our Galaxy in its Infancy, as Traced by Gaia and Complementary Spectroscopic Surveys. Please turn off your microphones and cameras during the talk. And if you have a question, you can write it down in the YouTube chat, and then we ask the presenter, or you can raise your hand here in the Google Meet, and the questions will be done after the presentation. So, Paola, whenever you are ready, you can start.
Okay, so thank you, Maria, and thanks all of you for this invitation. So, as you said, I'm going to talk about our galaxy, and in particular, what we are learning about the first billion years of evolution of our galaxy, thanks to the Gaia mission and complementary spectroscopic surveys. So as you all well know, you have seen probably many times this kind of artistic view of our galaxy. You know that is a spiral disk galaxy with a stellar bar in its center. And the sun is located in the disk, halfway between the center and the outer parts of the disk. And on the right, you have this edge-on artistic representation of the Milky Way, where you see the disk, you see the bulge, you see all these little dots that are globular clusters that are mostly in the halo of our galaxy. And then you can see this very diffuse and component that surrounds the disk, which is the stellar halo. And so I will mostly discuss the stellar halo, in fact, and the reason why we are interested in studying the stellar halo is because it's mostly made of stars which are metal poor, and so possibly very old. So if we want to learn something about the first billion years of evolution of our galaxy, it's possibly in the halo that we have to look for this. Now, this is an artistic representation, but if we look at really how the halo of our galaxy looks like, you see here on the top this very famous figure that is called the field of stream. So it's a portion of the halo of our galaxy where you see that the halo is not smooth at all, but there are plenty of substructures, like the monoceros ring, which is a stellar structure that is in the outskirts of our disk. And then the halo is also dominated by this Sagittarius stream that is made of stars that have been stripped from the Sagittarius dwarf that you can see here better on the bottom panel. That is a dwarf galaxy that is currently being accreted by the Milky Way. So we see structures, we see streams in the stellar halo, and these structures are trace current and recent accretion events. But one of the problem is to try to identify stars that have been accreted in the galaxy long ago, and that now cannot form any more coherent structures as those that you see here. And we need to reconstruct the ancient past of our galaxy for many reasons. And I think that every one of us has his own questions to answer. But for example, we want to understand how typical the accretion history of our galaxy has been if we compare, for example, it to model predictions or observations of galaxies of similar size and mass. We want to understand to what extent these accretions contributed to the mass and size growth of our galaxy, the role that these accretions had in boosting or suppressing the star formation in the Milky Way, and the connection, for example, between the accreted and the populations that formed in the Milky Way itself, that we usually call the in situ populations, and to what extent the properties of the galactic stellar populations that we see today are an heritage of past accretion events. So how to do it? How to find these old accretion events in our galaxy? So here you see a little movie where the different colors represent different satellites. This is a simulation made by Bullock and Johnson several years ago now, where you see the satellites interacting in a Milky Way-like potential. So you don't see the analytic potential of the Milky Way. You see only the satellites orbiting around. And you see that over time, the satellites are stripped of their stars and are completely destroyed in the Milky Way potential. So, and you see that they lose completely their coherence. You don't see any more streams. At some point, they are completely mixed in the galactic potential. So it means that it's not possible to recover these ancient accretions if we only look, for example, at a spatial coherence, at streams in the sky, because they won't form any more streams. We need other tracers. And one of the first suggestions was to look at the kinematics and of stars. The idea was very simple and very nice at the same time, and it was proposed at the end of about 20 years ago by Elmi and collaborators. So what they did was to run numerical simulations like the one I was showing before, and what they pointed out is that you can see it in these plots, for example, on the top. So each color here represents stars of a different simulated satellite. And what they showed is that at the beginning, for example, these stars, each satellite will group in a given region of the energy angular momentum space. So here we are not anymore looking only at spatial distribution of stars, but we are really looking at their distribution in so-called integral of motion spaces, like the orbital energy and the angular momentum. So each satellite is a clump, is a group of stars in this plot. But then they evolved the simulation for several billion years, and what they found is shown on the bottom, and it indicates that even after several billion years of evolution, the satellite stars could maintain their energy and angular momentum. That means that each clump, essentially, at the end of the simulation, could be identified with a different clump at the beginning of the simulation. Thus meaning that if we look, essentially, for clumps in energy angular momentum space, each of these clumps could represent a different progenitor galaxy. So these, in a spatial distribution, these stars would be completely mixed. It wouldn't be possible to see really streams in the sky, but still they keep a coherence in energy angular momentum or a different projection of the angular momentum space as shown on the right. And this idea, this suggestion was already at those times quite successful because, in fact, in the same years, using this idea, Elmi and collaborators could identify a group of stars in a solar vicinity volume. So these were stars for which they had distances and velocities, of course. So they could reconstruct their distribution in angular momentum space. So here you have the vertical component of the angular momentum, so the component perpendicular to the galactic disk. And here you have a combination of the other two components, so the perpendicular to the Z component. And in particular, they identified a group of stars which seems separated from the rest of the distribution. And because these stars was grouped in this integral of motion space, they suggested that these stars could be associated to an ancient accretion event. So they could be accreted stars, stars coming from a satellite. And indeed, they ran some simulations of this accretion, and they exactly show what I was saying before, that at the beginning, these stars in a spatial distribution show a stream, but after several billion years, these stars are completely mixed. still they could be identified in angular momentum spaces. So on the basis of this simulation and on the size of the clump, essentially, they suggested that stars associated to this clump that is now identified as the Helmi stream could belong to a satellite of about 10 to the 8 solar masses that was accreted by the Milky Way about 8 billion years ago. Now, this is not the only way. So we have the kinematics as a possible way to identify ancient accretion in the galaxy, but we have also the information that comes from chemical abundances. And the idea behind this is simple, even if it's not always so easy to identify things, as we will see. But the idea is, for example, to use the abundance of elements like, for example, oxygen over iron or silicon over iron, magnesium over iron as a function of metallicity. And so-called alpha elements as a function of metallicity. Why this? Because if we have a stellar population, and this stellar population over time, the stars making the stellar population will evolve. The most massive stars will explode, for example, as type 2 supernovae, releasing to the interstellar medium elements, alpha elements like magnesium, silicon, oxygen, and also iron. And so the ISM will be enriched by these elements, and so the new generation of stars will form in an ISM that is increasingly enriched in these elements. And this is the first part of this evolution, which is essentially flat, because these type 2 supernovae are releasing essentially as much as alpha elements as iron. But as soon as type 1 supernovae starts to form and explode in the galaxy, this type 1 supernova will release essentially iron. And this means that this alpha over iron or oxygen over iron abundance will start to decrease. So when we see a knee in a distribution of chemical abundances of a given stellar population, this knee essentially indicates the level of Fe over H that is reached by this population or environment before the type 1 supernovae starts to explode and enrich in iron the ISM. Now, the point is that populations that have different star formation histories produce different tracks. It means that the knee can be found at different level of metallicities. And this is exactly what we see in the Milky Way. If we compare here, you have a plot taken from a review by Elin Tolstoy and collaborators. In gray, the gray points corresponds to stars belonging to the Milky Way. Here you have, for example, you can look at the top panel, which is magnesium over iron as a function of metallicity. So the gray points are stars in the Milky Way. Here you have the disk, and here you have essentially the halo below metallicity below -1, let's say. While the color points corresponds to the stars that are currently in dwarf galaxies, so in satellite galaxies of the Milky Way. And what you can see is that different colors correspond to different dwarf galaxies, satellites of our own galaxy. But you can see that these galaxies show different chemical tracks in these planes. And in particular, you can see that at a given metallicity, stars belonging to satellite galaxies, less massive than the Milky Way, tend to have a lower content in alpha elements, like, for example, magnesium. This suggests a way to look for accreted stars in our galaxy. If we are able to find stars that are today in the Milky Way, but that show at a given metallicity a lower alpha enhancement, there is a high probability that these stars did not form in the Milky Way itself, but that were possibly accreted in the past from satellites. And this is exactly what Nissen and Schuster did in 2010. So what they did was to look at a sample of stars at the solar vicinity, few hundred parsec from the sun. So we are really looking at the very local volume around the sun. And for these stars, they had very good spectroscopy, and they could show that, in fact, if they selecting stars as halo stars on the basis of their kinematics, so essentially their orbits, they could show that these stars in this plane are not only redistributed in a kind of flat high sequence here in blue. But there is a secondary sequence of stars that is shown here in red that is made of stars that at a given metallicity value show a lower alpha enhancement. And because of the similarity of this kind of trend with the trend that we have seen for dwarf galaxies, Nissen and Schuster concluded that possibly these stars that are here shown in red did not form in the Milky Way itself, but they were accreted, and possibly were accreted, so are the remnants of a satellite accreted several billion years ago. So in few words, this was the state of the art, let's say, or some of the works and some of the discoveries that were made before Gaia and more recent spectroscopic surveys came out. So we had some indication of the existence of stars, even at few hundred of parsecs from the sun, that were possibly accreted. And the other point that I want to make about the Nissen and Schuster discovery is that these stars, these red stars that were suggested to be accreted, and the stars that are shown here in blue that were suggested to be stars formed in the Milky Way itself, do not only show different properties in this diagram, but they also show different kinematics. And so what is shown here on the bottom right panel is a plot that we will see later on. So I will spend 1 second to explain it. It's a plot based on the kinematics of stars, or essentially on their velocities. So on the x-axis, you have the velocity of stars relative to the local standard of rest. So essentially a star that rotates like the local standard of rest is placed here at 0, and stars that rotates more slowly than the local standard of rest tends to be on the left of this panel. And because the velocity of the local standard of rest is about 220 kilometers per second, at least this is the value they used, once you find velocities lower than minus 220, the motion is retrograde. So this vertical line divides stars that rotates in the same direction as the sun and the disk of our galaxy from stars that rotates in opposite direction. On the y-axis, you have the quadratic combination of the other two components of the velocity. So here you have the azimuthal velocity on the x-axis, and on the y-axis, you have the radial component of the velocity of a star and the vertical component. So essentially here you have stars that rotates like the disk, and as you go on the left and you go, for example, up in this plot, you are moving from a disk-like kinematics to a halo-like kinematics. So what you can see is that the red and the blue points do not redistribute in the same way in this diagram. And so you have that the blue points tend to be halfway, let's say, between the disk, the thick disk, and the red points. While the red points, so the accreted stars, tend to have either null rotation or retrograde rotation. So even in terms of kinematics, there was on average a difference between this population shown in red and the blue population shown in blue. So another indication that possibly the origin of these two populations was different. And so now we come to Gaia. And you all know what Gaia is the astrometric mission of space mission of ESA, the European Space Agency. And the aim of Gaia is to deliver, in fact, an unprecedented mapping of our galaxy by counting more than 1 billion objects in the sky, estimating their distance from Earth and their proper motions. And together with the astrometry and the photometry, Gaia is also delivering the largest catalog of line-of-sight velocities for stars in the galaxy and beyond. Having the position in the sky, the distance from the sun, and the proper motions and line-of-sight velocity for a subset of all Gaia stars, we can reconstruct the 6D position of stars. So 3 dimensions coming, spatial dimensions, plus the 3 dimensions related to velocities. And so really to have a clear view of how galaxies, how stars are redistributed in the galaxy and how they move in the galaxy. So you know that there have been several catalogs already published by Gaia, the Gaia collaboration. And there has been, the last one has been the early data release that has been released in December 2020. And just to give you a few numbers, it contains angular positions for about 1.8 billion objects in the sky, parallaxes for 1.4 billion, proper motions for 1.4 billion, and line of sight velocities for a bit more than 7 million stars. So we have a sample of 7 million stars for which we can reconstruct the whole phase space information. Now, one of the first things that was done with this Gaia, with all these data, for which we had also the line of sight velocity information, was essentially to place all these about 7 million stars in a diagram like the one I was showing you before. So here on the x-axis you have the velocity, the azimuthal velocity of the stars, and on the y-axis you have a combination of radial and vertical velocity. And here you have stars that rotate as fast as the disk. And here, as you move on the left and up, you have stars that start to have kinematics more typical of the halo. This plot was presented in this paper by the Gaia collaboration led by David Katz. And one of the things that was very interesting of this plot was this structure here. So you see a kind of vertical structure that is more or less centered around azimuthal velocities of 0. That means very radial motions, because essentially the azimuthal velocity, yes, the average value is 0. And one of the questions was, what was the origin of this structure? And contemporary to that, there was another paper coming out from the Gaia collaboration that was led by Karim Babuzio, in which the HR diagram of Gaia stars was studied. And in particular, one of the plots of this paper showed the HR diagram of stars that have halo-like kinematics. So let's say essentially stars that are in this part of the diagram. And one of the interesting things that you can see, and it was unexpected in fact, is that when you select stars on the basis of their kinematics to be halo stars, you see that you don't obtain a unique, let's say, or a uniform sequence, but you can clearly see two sequences in this diagram. And so what the question was, what is the why do we have two sequences among halo stars? What is the origin of that? And so after the publication of the Gaia second release, because these results came out with the second Gaia release, so in April 2018, we started to investigate a bit more the origin of this double sequence in the HR diagram, and so studying at the same time their distribution in the HR diagram, but also the kinematic and chemical abundance properties of the stars. So here you see a way to proceed. We separated we looked at the two sequences in the HR diagram that I will indicate as the blue sequence and the red sequence in the following of this talk. And then we try to see how these blue and red sequences were distributed in the kinematic plot I was showing you before. And you can see that most of stars belonging to the blue sequence are essentially redistributed along this vertical structure that I was showing you before, while stars on the red sequence are mostly distributed halfway between stars with disk kinematics that are here and the stars with the blue belonging to this vertical sequence. As you see, there is an overlap between the two, but on average, their kinematics is different. And we could also study how this blue and red sequence appear in a magnesium over iron metallicity plane, because as I said before, this can also help in distinguish populations that have a different origin. And here you can see that, again, on average, there is an overlap between the two sequences, but on average, you see that stars belonging to the red sequence tend to have higher magnesium over iron content than stars belonging to the blue sequence, especially at metallicity below, let's say, minus 1.2, so really at the end. And this was, apart from the colors that are inverted, but it was essentially the same result that was already found by Nissen and Schuster. So the existence of these two sequences at the solar vicinity. Only that in the case of Gaia, we are seeing this sequence on a larger scale. So on the basis of that, the kinematics, the properties in the HR diagram, the abundances, what we proposed in this paper led by Misha Haywood was that the blue sequence stars seems to constitute a significant fraction of all stars with halokinematics, and that they could be on a chemical track that is less alpha enriched than disk stars at the same metallicity, and for these reasons we thought they were compatible with an accreted population, and essentially the same accreted population that was already identified by Nissen and Schuster. In the same few weeks after this paper, there were, of course, you can imagine, once all these data are released, there is a rush to analyze and to get results. And so only a few weeks after, there was another paper led by Helmi and collaborators, which essentially reached the same conclusion, also making some comparison with using apogee data for the comparison. And what they concluded is that the inner halo is dominated indeed by the debris of an object which was probably more massive than the small Magellanic Cloud at the epoch of the accretion, and that was named by this author as Gaia Enceladus. And here again, you see a plot similar to the one I was showing before, where you clearly see that most of the stars that are related to this Gaia Enceladus are in fact on the low alpha sequence. Now, sometimes the nomenclature can be confusing because we can refer to Gaia Enceladus also as Gaia Sausage, and the reason for this second name comes from the fact that already using data from the first data release, so about a year before the release of the second Gaia catalog, Belokurov and collaborators, on the basis of the kinematics only of stars, of halo stars, identified stars that are shown here in a kinematic plane. So here is the galactocentric radial velocity, so the velocity with respect to the galactic center, and here is the azimuthal velocity, so the rotation of stars. So what they did was to select all stars in this range of metallicities, and what they showed is that part of these stars are redistributed along a line which coincide with azimuthal velocity with mean 0. Okay, and they also it's this horizontal structure that is nothing else than the vertical structure that we see here. So they call this structure like the Gaia sausage because they said they reminded a kind of sausage-like shape, but essentially is the same structure that then was identified as Gaia Enceladus. So we are possibly talking about the same object. And Belokurov concluded on the basis of some comparison with simulations that possibly the epoch of accretion of this Gaia sausage satellite was to be placed between 8 and 11 billion years ago. Now, again, this is simply a comparison of the Gaia DR2 diagram, what we call the Tumore diagram, this kinematic diagram I have been discussed already. And overlap to this diagram, there are again the Nissen and Schuster star, just to show you that these early results by Nissen and Schuster are really consistent with what we are seeing now with Gaia, of course, with many more stars than the one they could analyze. Now, so we have seen that there are indications of the accretion of a satellite, at least of a satellite, and one of the questions we can ask, and possibly the satellite was massive, and one of the reasons is the characteristics of the low alpha sequence that we see in the abundance plane plot. So we think that this Gaia sausage must have been possibly about 1/10 of the Milky Way at the time of the accretion. And we know that when a satellite as massive as Gaia sausage is accreted on a disk galaxy like the Milky Way, we expect the disk of the Milky Way to be damaged, and in particular to be eaten up by the accretion. And this has been shown, for example, by many, in fact, over the years. So these are numerical simulations, and this is a plot taken from simulation by Purcell et al. In 2010. And what is shown here is this galaxy before accreting a satellite. So you see a disk, essentially, with a bulge in the center. And then what you have on the middle and the right panel is the distribution of stars in the galaxy after the accretion ends. And in particular, in the middle panel, what you see are stars that initially were in the disk of the main galaxy, so let's say the Milky Way galaxy, after the accretion. You see that you still have a disk, but there is also a low density population of stars that have been ejected from the disk and then are populating a thick disk and a halo. And on the right, you have the distribution of stars that have been accreted. So stars that were initially in the satellite that at the end of the accretion are redistributed in the halo. So you see that the puffed up population, so the heated disk, can represent a significant fraction of stars, especially at, let's say, in the inner 10-20 kpc of the galaxy, at least in this simulation. So at a satellite, the point I want to make is that we expect from numerical simulation that a satellite as massive as Gaia sausage and Enceladus must have induced damages on the galactic disk at the time of the accretion, for example, ejecting disk stars at large heights from the plane in the stellar halo. So the question was, is it possible to find the signatures of this kinematic heating process and to try to use this signature to date the end of the accretion of Gaia sausage and Enceladus? And so this is what we tried to do in the data. And so what I'm showing here, sorry, it's a bit slow. I don't want to show you the movie. I would like to move to the next slide. But in the meantime, I can show. This is simply a movie of the accretion of a satellite galaxy on a Milky Way like galaxy. So to show you how the disk can puff up during the interaction. But okay, I want to come to this. So on the basis of this indication and suggestions coming from simulations, we decided to look again into the data and to cross-match Gaia second release with spectroscopic data coming from the Apogee survey. So in total, after this cross-match and taking only stars with the best parallaxes and making some quality cuts, we arrived to analyze a sample of about 7,000 stars. And what I want to show you here is this plot that is a bit complicated, but I hope not too much, where you see on the x-axis the metallicity of the stars, and on the y-axis, you have again the azimuthal velocity. So the rotation, the velocity rotation of the stars. And on the bottom, you have stars with negative velocities in this plot indicate stars with prograde motion. So let's say stars that rotate in the same direction as the disk. While stars with positive velocities are stars that have retrograde motions. That is, stars that rotate in opposite direction. And at the beginning, don't look at the colors. The colors indicate the magnesium over iron content of each of these stars. But for the moment, you can simply look at the overall shape of this plot. And what you see is that essentially the yellow star indicates the position of the sun, just to give you an idea where the sun would be located in this plot. So the thing that I would like you to retain is that when you look at stars with high metallicities, let's say above about -0.3, you see stars that have a prograde rotation and not so much different from that of the sun. While when you start to look at stars that are at metallicities of -0.3 and below, you clearly see that there is something that happens at this point, because you start to see stars. The kinematics is not only anymore the kinematics only of disk stars. You start to see stars which have null velocity or retrograde motions. But these stars here have the same metallicity and the same alpha content of stars of the disk. So these are stars that have, from the point of view of chemical abundances, the same characteristics of disk stars, but have very different kinematics, have halo-like kinematics, but abundances compatible with a disk population. And this for us was the smoking gun of this heating effect that was predicted by simulation, because we were exactly finding this population of stars with hot kinematics, but disk-like chemical abundances. This is why it's very important to have also chemical abundances to try to separate or associate populations that apparently look different. And so we call this kind of structure the plume in this V-phi metallicity space. And on the basis of the characteristic on the magnesium over iron abundances at which this plume appears, we could date the epoch at which the Gaia Sausage Enceladus and possibly the most massive accretions ended in the galaxy, because it's essentially the epoch where most of the heating of the disk ends. And we dated this epoch to occur between 9 and 11 billion years ago. So these 10 billion years ago plus minus 1, in fact, sets a time limit to the accretion of Gaia Sausage Enceladus and to the early accretion and most violent, let's say, accretion experienced by the Milky Way. These conclusions were confirmed just a few weeks, I think, after by Belokurov et al. 2020. So if you have heard about the splash, as Belokurov called this structure in this heating of the disk, this structure is essentially what we call the plume. So we are looking, it's nice because two different, let's say, works arrived to the same conclusions, that we were really seeing the signature of the heating of the galactic disk. And then there have been several other works that have looked at that. I would like simply to cite also this work by Gallart and collaborators, who arrived to similar conclusions based this time on the analysis of the HR diagram of accreted stars. Now, I think I have very few minutes left, so I would like simply to mention a few other accretions, because there is Gaia Sausage Enceladus, which occupies a large portion of the halo, at least for the portion of the halo that we can analyze and see today. But there have been other accretions that have been possibly discovered in the Gaia data. So there is the Sequoia Remnant. What is Sequoia? Sequoia is a structure that has been identified, again, in the energy angular momentum plane by Myong and collaborators, and corresponds to stars that have very retrograde motions. They are shown here in this plane, and while the sausage Gaia Enceladus remnant is here. So because of their different kinematics, it has been suggested by Myong that the stars, so the disk, just to help you place the main components of the galaxy, the disk is here. Huh? So these are really stars with retrograde motions and larger energy than those of the stars. And because of the peculiar kinematics, Myong et al. Have suggested that this is a second substantial accretion episode experienced by the Milky Way that may be distinct from the Gaia Sausage, also because of the different mean metallicity of stars in Sequoia. And it should, this Sequoia star should correspond to a satellite that was less massive than the Gaia Sausage, but that should have been accreted more or less at the same time. And so if you want to have a summary of some of the main accretion event possibly experienced by our galaxy, and here I'm talking about accretion events with mass ratios above 1 to 100, so where the satellite was at least 100 of the mass of the Milky Way at the time of the accretion. Here you have this very nice merger tree that is taken from a paper by Krusen et al. 2020, where what you see is the Milky Way here. And the color is the mass of the Milky Way that increases with time. So here you have the look back time. So here we are today, and here is 12 billion years ago. Here you have redshift, and the different symbols corresponds to different satellites. So we have seen Gaia and Enceladus that should have been accreted about 9 billion years ago. You have the Elmi stream that we have mentioned. You have Sequoia. You have the Sagittarius, which was accretion is still going on. And then you have this other satellite that is called Kraken that I didn't have time to look at, to discuss, but you can see reference. If you are interested, you can look at this paper by Krusen and collaborator. So this is a possible merger tree of the Milky Way. And there are many other, these are the main structures, but there have been many other structures that have been identified in these energy angular momentum plots. And for example, Wukong, Arjuna, Itoi, Tamnos, so Aleph. So there are plenty of different substructures that have been identified in this plane. And one of the point and of the difficult point is now to understand to what extent all these substructures are really due to different and independent accretion events, or how much we are seeing stars belonging to the same accretion event that have been redistributed over a large interval in this energy angular momentum plane. So I finish really with these last few slides about, in fact, how unique is this merger tree that we are trying to build for our galaxy. And one of the reasons why I'm discussing this is that a few years ago, we ran a set of simulations of the accretion of satellite galaxies on the Milky Way. Here you see simply some of these plots at different time, edge-on and face-on view of these accretion processes. So you can see that the disk of the Milky Way type galaxy can be extremely distorted by the accretion. But one of the things we looked at was how satellite stars redistribute in this energy angular momentum plane during the interaction. And here you can see in 1 second the movie of this. So you start with all satellite stars in a given region of the energy angular momentum plane. And then you will see, so the inset is the distance between the satellite and the Milky Way as a function of time. And what you see is that while these satellite galaxies orbit around the Milky Way type galaxy, the satellite loses part of its orbital energy because of dynamical friction. Then it tends to go deep in the potential well of the Milky Way, and it leaves stars at different level of energy. So you can see several clumps in this space that all originate in the same satellite, but there are simply stars that have been lost by the satellite at different times during its orbit. And this poses a problem in the way we interpret this energy angular momentum plane, because if I remember at the beginning, I was saying different clumps corresponds to different satellites. This was the early suggestion. That means that if I count the number of clumps that I have in this space, I can try to reconstruct the number of accretion the Milky Way experienced over time. But if the satellite is massive enough, as it was the case in our simulations, and the mass ratio is more or less the one expected for Gaia, Sausage, and Enceladus, you see that one satellite can produce several clumps. So you cannot anymore say one clump or one satellite. And this poses a number of questions that, if you want, we can discuss in the questions, but that are related to the interpretation of Sequoia, that are related to the interpretation, for example, of the Elmi stream. So I leave you with my conclusions. There is evidence of at least a significant merger experienced by the galaxy about 10 million years ago that is called Gaia, Sausage, and Enceladus. And we have seen that the precursor of this discovery was already in the data, for example, analyzed by Nissen and Schuster 10 years ago. The interpretation of other structures that are found in the integral of motion spaces is still open. They could be associated to the same merger event, that is to Gaia, Sausage, and Enceladus, and not to be independent minor accretion. And this is something that we really, for which we need really possibly to look more in detail to chemical abundances to try to separate these accretion events if we can. And the galaxy experienced the last significant epoch of disk eating between 9 and 11 billion years ago. And this finding helps constraining the time of accretion of Gaia Sausage Enceladus, that say the time where the damage of the accretion of Gaia Sausage Enceladus on the Milky Way disk ended. And I've not talked at all about the last discoveries about the very metal poor and ultra metal poor stars, and I will leave you some references if you are interested, or we can discuss during the question time. Thank you for the attention.
Great, thank you very much, Paola, for this wonderful talk. I will start the discussion on the questions with a question. I was curious on how do you determine that in this HR diagram that you show of the stars of the halo, that there are actually two sequences. What is the criteria that you use to separate both?
So the fact that the idea that there are two sequences came already in this paper by Babusiu. So you see, so these are stars selected to be halo stars, kinematically selected as halo stars, and you see at least, let's say, two main sequences. Here you can see, for example, when you look at this part of the HR diagram below the turn-off, but also here, you see clearly that there are these two different sequences. And then the way we separated these two sequences was simply using an isochron to divide the two. Okay. Now, the point is that there is clearly, maybe I complicate too much the thing, but once you recognize that this sequence is mostly related to accreted stars, and this sequence is mostly made of stars of the disk puffed up by the interaction, it doesn't mean that there is no contamination of disk stars also in this sequence. But it simply means that on average, these two sequences are made of different populations.
Okay. Yeah, I understand.
Okay.
Yes.
So there is an overlap that indeed you see everywhere. You see in the kinematics, you see also in the chemistry, because below -1, essentially, if you take an alpha over iron metallicity plane, it starts to be difficult to distinguish these two sequences because they start to overlap in alpha over iron. So there is indeed possibly a disk that extends, and we know that already from several works made in the past and more recent works, that there is possibly a disk extending also below -1. So there is in metallicity. So there is clearly an overlap of all these populations. But on average, there is this significant low alpha population that is associated to at least Gaia Sausage Enceladus, at least one accretion.
Yes. Okay, I see. Yeah, I understand. So the thing is that you do not need actually to pick and say, okay, this star is from this one, or it's clear that there are two, and yes, they are contaminated by both types. So,
there are at least two, and in fact, there is something interesting that was already discussed in Nissen and Schuster. I love this work because I really think that. There were, how many? Less than 100 stars, and they already could derive many of the results that we are finding again, okay? And one of the points they raised was that the low alpha stars may have been accreted, and as we said, but that the dispersion in abundance ratio that given Phi over H suggests that these satellites followed somewhat different chemical evolution tracks. So in fact, they suggest also the possibility that what we are seeing here is not a unique satellite, but possibly in this low alpha sequence there could be hidden several satellites with slightly different masses. So this is something that is difficult to disentangle given the uncertainty that we have on the chemical abundances. It's difficult to make the difference, but we need to keep it in mind that we call it Gaia Enceladus, but it can be several satellites in fact.
Yeah, I understand. Okay, thank you. Let's give time to other questions. So, Reinaldo, you can ask your question.
Thanks, Paulo, for the talk. Found it very clear. I have two questions. First is during these major events of merger, is it expected the Milky Way to have some bursts of star formation, or?
Yes, it is possible, and there have been also work suggesting that one can find, let's say, the traces of these burst events in the Milky Way disk. And we see it also from simulations. Now, how much you can stimulate star formation during an accretion event is debated, and I think is debated also if I look only from the numerical point of view. And I think that one of the reasons why it is debated is that it also depends on the parameters of the accretion, on the mass of the satellite. There are plenty of parameters that can play a role. But you can stimulate the star formation also because you are adding new gas to the system. The satellite will bring its own gas, especially for satellites accreted at early times that were possibly very gas rich, and so indeed, I mean, what we see, that what we think we understand is that possibly all the early disk has been formed in a kind of very intense phase of star formation. Now, the point is to understand to what extent this intense star formation has been sustained by the accretion events. But it's something that is difficult to separate. But it's for sure that the first billion years of evolution of the galaxy has been the most intense from the point of view of star formation. So it can have to do with the fact that it was the most active epoch of accretion.
Do you think there is some chance also to detect some observable of this the epoch of this star forming bursts? I don't know, by maybe by the count of compact objects formed during that time, matching with the
possibly age. Or yes, or possibly maybe in the future also, if we I think maybe if we will be able really to look more in detail to the distribution of alpha over iron elements in the 4 stars that are, let's say, old, right. To try to see if there are several peaks or what's going on there. Yes.
Yeah, very interesting. Something, another evidence independence. I have another question. Is about what some doubts I had in the beginning. You talked a little bit by the end of your talk about what's necessary to destroy the structures in the phase space of the energy angular momentum, and we showed that in these events of merger, depending on the ratio of mass of the satellites, you can somewhat wash these structures, right? So, if I understood correctly, just to check if I understood it, these structures will be washed. It's just a matter of timing. Is it so?
It's a matter mainly of mass of the accreted satellite. Why is that? Is because the main effect that you see here, I mean, to have a merger, for example, to have a massive satellite that merged with the Milky Way, typically you need the dynamical friction. That is, you need that some of the orbital energy of the satellite is lost and is given to the Milky Way field stars. So what you see here, the reason why you start here and move down is because of dynamical friction. So the satellite, it keeps orbiting around the Milky Way, it loses part of the orbital energy, and so the remaining stars, the stars that are not lost in the initial phases, will tend to go deep in the potential well of the galaxy. Sorry. So what changes with respect to the plots on the left is that first in this simulation, early simulation, dynamical friction was not taken into account. So the energy in some sense was conserved by definition. There was no possibility for the satellite to redistribute part of its orbital energy to field stars. So this is a point. And then the second point is that even when you take into account dynamical friction, the effect of the dynamical friction will depend on the mass of the satellite. So the more the satellite is massive, the more it will suffer dynamical friction in a given amount of time. So essentially, low mass satellites can still be seen as clumps. But satellites which have a mass ratio 1 to 10 of the Milky Way, no. Unless they disperse immediately, otherwise they will tend to penetrate in the inner region of the Milky Way, and at each pericenter passage, they will lose part of their stars. And so this is why you see such an elongated structure with all these clumps. I don't know if it's clear.
Yes, and I believe dark matter plays
yes,
a role to complicate the picture, the clumps of dark
indeed.
matter.
I mean, indeed, there is dark matter in this simulation, and the dark matter is the first, let's say, the first component that acts and is responsible of this dynamical friction, because the satellite, before intercepting the baryonic disk, will orbit in the dark matter halo. So part of the orbital energy of the satellite is absorbed by dark matter particles, also part of the angular momentum, no? And then, as the satellite loses part of its orbital energy, it will penetrate deeper and deeper in the inner region of the Milky Way. And at this point, you start to have dynamical friction also by the disk and eventually by the bulge, etc.
Thank you, Paola.
Yeah, you're welcome.
Okay, thank you, Reinaldo. Laert, you can go ahead,
Very
please.
nice talk, Paola. I have a curiosity. What is the fraction of the Milky Way mass that is due to the accretion of these satellites? 5%, 10%, or less?
Okay, so I may answer like this and say if the stellar halo of the galaxy is estimated to be few percent of the stellar mass. So if we make the hypothesis that all the stellar halo is accreted, which possibly is not the case, we could conclude that few percent of the stellar mass of the Milky Way is accreted. But there is a problem, is that what we see here, for example, let me take one of these plots with, for example, this one. So the problem is that this few percent essentially is what you see here. But if the Milky Way
not showing
accreted,
I don't think you're sharing.
oh, sorry,
Yeah.
I have to share again, but it's shared for me. And to try again. Up. Let's try to see. Okay, so now we try again. Can you see it now? That's strange. Up. Otherwise, I will tell you without showing you the plot. The problem is that, yeah, because I'm not. Okay. Can you see it? Oh, that's strange. Well, I will try to tell you without showing. The problem is that if you can see stars which have different, for example, chemical abundance properties. In the idea that the stars are associated to satellites that are less massive than the Milky Way itself. But now, if you think that you have accreted in the past something that is similar in mass to the mass of the Milky Way at the time of the accretion, you can also expect that these stars will have chemical abundances similar to the one of the Milky Way. So among the disk stars, for example, or all the disk stars, it's difficult to say all these stars formed in the Milky Way, and this is a possible answer, or these stars partially formed in another galaxy which had a mass similar to the Milky Way at the time of the accretion, and so now they are it's difficult to identify them in chemical abundance planes because we expect them to have tracks similar to the one shown by Milky Way stars. So there have been simulations, for example, some papers by Florent Renaud, which were published last year, where he was showing exactly this, that you can have a major accretion, so the accretion of a galaxy with a mass similar to the Milky Way that may be accreted at high redshift, and essentially it will, the stars of this accretion event would redistribute essentially where we identify in situ stars of the Milky Way. So it's difficult. I mean, so it means that the answer can be few percent, but it can also be that a significant fraction of what we call the disk of our galaxy, of the thick disk of our galaxy, may have been formed in another galaxy later on accreted by the Milky Way. And at this point, it's difficult to make the difference because we don't know how to make the difference.
Okay, thank you.
Okay, so Guilherme.
Hi. Thank you so much for your talk, Paola. I think it was pretty useful and it was pretty didactic for people.
Thank you.
So I can recommend, for instance, the undergraduate students.
Thanks.
So this will be very useful. So the question that I have is, well, one of the questions was the one that Reinaldo asked, so I think this is answered already. But the second one is, how do you go from the plot that you show of V5 versus F1H versus metallicity, colored by the alpha over iron? How do you go from that to dating the Gaia Enceladus merger? Is it in comparison with the simulations that you run?
No, it was all based on data. Now I think, oh yes, I have it. Okay, I have everything. So another way, so this is the plot where I can show it here. There are less text. So this is the plot we are talking about, where the colors indicates the magnesium over iron content. So in my slides somewhere, I have.
Yeah, we are not seeing, but I remember the plot, so I guess you can go ahead.
And so the idea is that you can see the discussion in my paper from 2019 if you want to look at all the plots. But the point is that it was possible to identify the magnesium over iron level at which you see this heating effect. It's not only that appears at a given metallicity, but it also appears at a given magnesium over iron level. And in 2013, we published, so the first author is Haywood, and I'm among the authors. We published a paper where we were showing that there exists a relation between the age of stars at the solar vicinity and their magnesium over iron content. So once we identify the magnesium over iron value at which we see this heating effect, we use this relation to convert magnesium over iron in age.
Yeah, okay. Yeah, but I guess now that you said that you can relate when, at which level of magnesium over iron this heating effect starts to show up, I guess it's already kind of solved because the ages of thick disk stars are so uniform. For instance, the chemically defined thick disk, they are basically all around 10 gigayears. So yes. I guess this would be another way to go about it. For instance, just
yes. We yes. Yeah, sure. So if I reload, possibly I will be disconnected. No, I don't know. I'll try. Ok, let me check.
Ok. Isso é bom também que fica na gravação, né?
I think that now you can see it. Is it possible? Can you see it?
Yes, we can.
Yes.
Okay, good. let me see. I had this relation somewhere. Okay, so this was the magnesium over iron age relation I was showing. Huh? Okay. So once we identified the level of magnesium over iron at which we see this heating, that is here, that is this essentially gray horizontal line, we could associate this to an age.
Okay. And, yeah, this is good now that you're showing this, because it stays on the recording of the talk, so it's pretty useful for people that will go watch it later on YouTube.
Yeah. Yes. So this was not shown in the talk, but it's all. I mean, it's in my backup slide, so I didn't go through this, but it's in this. It's shown again in this paper, but the original relation is taken from this paper, Haywood et al. 2013.
Okay.
Yes. Sorry. Up. Can you see it better? Okay.
Also, so the second question that I have, or the third, I guess, would be related to the several clumps when you have your simulation of the galaxy merging that you show several clumps in energy versus angular momentum. The question that I have is, can we relate, for instance, the portion of the accreted galaxy that is deeper into the potential? For instance, can we say that these stars that reach deeper into the potential of the Milky Way, like galaxy in the simulation, are those related to, for instance, I don't know, the core of the galaxy that is accreted, or the edges of the galaxy? I don't know. Because that would be useful, for instance, if we can compare to, I don't know, metallicity gradients in galaxies at high redshift.
Yeah, so it's something that we are currently working with a student. That is, I expect that is essentially the less the stars are gravitationally bound to the satellite, the earlier on in the accretion event they will be lost. So I expect that in the potential well, you find essentially the part of the galaxy that resists all these tidal effects. But now what we are doing with the student is essentially to attach, because these simulations here do not contain star formation or chemical evolution, because in this case we were really interested in the dynamical effects. And so we are now starting to attach metallicity gradients to these satellite galaxies to see how stars of different metallicities redistribute in these plots. Because you expect that on average, stars that are in different parts of this plot won't have necessarily the same metallicity or the same alpha abundances.
Yeah,
so
if it's as massive as Gaia sausage.
Yeah, like for example, the Gaia sausage, and one of the questions is the relation between the Gaia sausage and, for example, Sequoia, to understand whether these are two different events or not.
Yeah. Okay, so I'll wait for the paper.
Yeah, it will take some time, because the student started few weeks ago, but it's an idea that I wanted to test, and so I hope to have some results soon about that.
Okay.
But yes, I expect that on average the metallicity won't be the same. The mean metallicity.
Okay.
Yeah. And in all these, you have also the in situ stars, which I have not shown in this plot, but they will also redistribute in this plot. So the disk of the Milky Way would be here, but of the simulated Milky Way will be here. But once the disk is heated by the interaction, part of the stars will end up here, and will also redistribute in a kind of clumpy structure. So it's really not easy to interpret these clumps, but also to differentiate stars of different origins. So this is why you really need the chemical abundances.
Okay, yeah, thank you so much for answering these questions. I think Reinaldo has another one. And thank you so much for the very didactic talk.
Thanks to you.
Thanks, Guilherme. Reinaldo?
I'll make a very quick question. I was very interested when you answered Guilherme, and you told about this work you are doing now about studying the effects of this star formation during the process. So I'm curious, is it necessary also to make a hydrodynamics together with anybody to take into account the effects on the gas, or is there some way more economic?
I think so, for many reasons. One is that, well, apart that at some point you would like to be as much self-consistent as possible. No, you were mentioning before the star formation that can be induced by the interaction, so you want to study these effects. There is another effect that is related to the heating of the disk, and it has been discussed in many works already. Let's say around 2010. And I'm sorry, I'm trying to remember the work in particular, but maybe at some point it will come to my mind, the name, but where they were using numerical simulations to show how the heating of the disk depends on the amount of gas that is on the main galaxy. The reason being that if the galaxy contains a large amount of gas, this gas will be, that is mostly redistributed in the disk, will counteract the heating effect. So for a given satellite mass for the same orbital parameters, if this satellite is accreted by a gas-poor Milky Way galaxy or a gas-rich Milky Way galaxy, the heating effect won't be the same. That is, the gas-poor galaxy will tend to be more heated up than the gas-rich counterpart. So for sure, this is something to do. You know, you always start from something. So the idea there was to try to have really simulations with a sufficient number of particles to be able really not only to see these dynamical friction effect, but also to be able to see all these substructures that you can see in phase space. But I agree with you that I mean, one of the next steps is really to run simulations which take into account the physics that is more complex than the one that I'm analyzing now. So here I can essentially see the effects on the stellar dynamics.
Right. Yes, very. I think it's a very interesting research. I also like Guilherme. I'm looking forward to see I think it's very interesting to answer these questions. Thank you.
Okay, so many thanks, Paola, again for your wonderful talk and for this great discussion. So I would like also to thank everyone who is following.
And thanks to all of you for the questions. It has been really very, very nice. And yes, feel free if you have any other questions or ideas you want to develop to contact me. I will be happy.
Thank you very much. It was our pleasure. Many thanks. So Richard, you can stop the transmission in YouTube, please.